So in today's session, we will discuss the iron carbon phase diagram. So this is very important topic as far as our course is concerned. If you study this phase diagram properly, then easily you can understand all other phase diagrams. The transformations which takes place in these diagrams are very important as far as our heat treatment part is concerned. So the iron carbon equilibrium diagram, it is the graphical representation of the changes in phase and structure of the iron with variation in temperature and the concentration of iron and carbon. So this diagram is the basis of the steel and the cast iron. So all the transformations taking place in an iron carbon alloy are represented by this diagram. So it indicates temperature ranges and percentage carbon in the alloy. It indicates the boundaries at which phase changes takes place. It also helps in understanding the basis and principles of heat treatment. So the applications of iron carbon diagrams is very important. The last application as far as our topic is concerned is very important. So as we know, the basis for all the phase diagrams is the cooling curve. Like in the previous session, we discussed how to plot the cooling curve by using thermal analysis technique. So you can see it here, cooling curve of a pure iron. And if you plot the cooling curve and if you look at this cooling curve of a pure iron, you can see it here. The first portion is liquid, then it is a solid portion, then again solid portion, solid like that. But you can see it here, the iron has different forms as the temperature changes. So initially it is a BCC structure at room temperature, then it becomes non-magnetic, then it converts into FCC structure, and again it transforms into BCC structure, and finally above 1535 degrees centigrade it transforms into liquid phase. So the iron is an allotropic material. So this is the phase diagram of a iron, but at different pressures. So far we have not discussed any part of pressure, but just for your information you can see at different pressures the iron also changes different crystal structures. So around room temperature, atmospheric pressure, it is a BCC structure. At higher pressure it transforms into HCP, and with high pressure and high temperature when it transforms into FCC. So means the iron has a different properties. Iron, it shows different crystal structure as the pressure and temperature changes. So that is the beauty of iron carbon phase diagram. If you study iron carbon phase diagram properly, you can study all the phase diagrams very easily. So you can see, so this is the iron carbon equilibrium phase diagram. To be very honest, so this is not the full phase diagram, because you can see it here. So this two vertical axis. So one vertical axis is a pure iron and second vertical axis should be 100% carbon, but here only 6.67% carbon is present. You can see it here, only 6.67% carbon is present. So means this is not a full phase diagram, this is a part of iron carbon phase diagram. Some literature suggests that this is a iron carbide phase diagram, and some people say that it is a iron carbon phase diagram only because carbon beyond 4.3% nobody uses. There is no application which shows carbon percentage greater than 6%. So that's why it is a part of phase diagram, but it can be considered as a full phase diagram. Okay. Now you can see it here. Horizontal axis is percentage of carbon starting from 0 to 6.67% carbon. Two vertical axis and both the words temperature. Now, as you can see it here, at room temperature we have room temperature 2 around 723. We have alpha In order to understand properly, I will go back to the next slide where you can see it very easily. Okay. So from room temperature to around 910 degrees centigrade, we have only one phase, that is alpha. Okay. So from here to 910 degrees centigrade, we have only one phase alpha. Then above 910 to 1400 degrees centigrade, we have another phase gamma, which is a FCC structure. Alpha is a BCC structure. Above 1400 to 1539 degrees centigrade, we have one more phase here, that is delta. So alpha, gamma and delta. So these are the three phases, you can see it here, and which is close to one of the terminal of the phase diagram. So that's why we call these phases as, obviously it is a solid solution. So these are terminal solid solutions, because so these solid solutions are close to one of the terminals of the iron carbon phase diagram. Okay, so this is alpha, you can see it here. So this arrow mark, alpha ferrite, gamma ferrite, gamma ion we call here FCC, and delta ferrite somewhere here we call it's a BCC structure again. So from room temperature to 910, we have only one phase alpha ferrite, but you can see all these are Greek letters, alpha, gamma and delta. But in Greek letters, alpha, beta, gamma, delta comes. Where is the beta ion then? You can see it here, alpha, gamma, delta. There is no beta ion. But if you see the literature, initially it was thought that iron from 768 degrees centigrade converts into non-magnetic. So initially people thought that it is due to phase transformation, iron has lost magnetic properties. So that's why the iron which is present after 768 degrees centigrade to 910 degrees centigrade, they called or they referred as beta ion. But later on they discovered that iron has lost the magnetic properties, not due to phase transformation, it is due to electron spin motion. So that's why they removed the name beta. And that's why you can see here alpha, gamma, delta. There is no beta ion present in iron carbon phase diagram. Okay, so that was the mistake. That was the due to not sufficient knowledge of the magnetic properties. Initially, people thought that it was the beta ion which is responsible for non-magnetic nature. But later on, they discovered that it is not due to phase transformation. It is due to electron spin motion and has lost the magnetic properties. So that's why they removed the term beta ion from there, and it whole becomes alpha. It whole becomes alpha up to 910 degrees centigrade, then gamma, then delta. And obviously these are the solid solution. Solid solution. This is not substitutional solid solution. This is an interstitial type solid solution. Why interstitial type solid solution? Because size of the carbon is less than 1 angstrom, and in combination with iron it forms an interstitial type solid solution. So you can see in this type of iron carbon phase diagram only 3 solid solutions are exist, that is alpha ferrite, gamma ion and delta ferrite. And these are terminal solid solution because these are close to one of the terminal of the phase diagram. So here also you can see, so this line is a solubility limit line. What is meant by solubility limit line? Already we have discussed. If you cross this solubility limit line, you will end up into 2-phase mixture. So similarly here we have solubility limit line. So means the solubility limit line, you can see it here up to 0.025 this point. So 0.025% carbon can be dissolved into the iron without forming second phase, and that is at 723, or in some of the literature it is 727 degrees centigrade. So means maximum percentage of carbon that can be dissolved into the alpha ion is 0.025 percentage, and that is at 723 or 727 degrees centigrade. If you cross this 0.025 percentage, you will get two phase mixture, that is perlite plus ferrite. But below 0.025 we have only one phase, that is ferrite. So means this is a solubility limit line. So maximum percentage of carbon that can be dissolved into the austenite region. So this phase we call gamma ion is a austenite. So maximum percentage of carbon that can be dissolved into this austenitic region is 2.06 or 2%, and that is at 1147 degrees centigrade. Similarly, the maximum percentage of carbon that can be dissolved into the delta ion is 0.15%, and that is at 1493 degrees centigrade. So means if you look at this solubility limit line or maximum percentage, if you cross this percentage, you will end up with the two-phase mixture. So here, if you cross 0.025, you will end up with perlite plus ferrite. Now, let us apply Gibbs phase rule to this iron carbon phase diagram. So Gibbs phase rule says that P plus F equals to C plus 1. C plus 2, but we will consider pressure as atmospheric. So P plus F equals to C plus 1. If you apply the phase rule, let us apply phase rule to at this point. That is 0.23 percentage carbon and 727 or 723 degrees centigrade. So number of phases here are 3. That is austenite, perlite and ferrite. And number of components equals to 2, that is iron and carbon. So how many phases present here? So P plus F equals to C plus 1. So F, we need to find out the F value. So number of components are 2 and C plus 1, that is C is equals to 2. So number of phases here is equals to 3. So P value 3, C value 2, and if you rearrange the terms and calculate F value, it becomes 0. So degrees of freedom at this point is 0. Similarly, if you calculate degrees of freedom at this point, that is 1147 degrees centigrade and 4.3% carbon is equals to 0. That is 3 phases liquid, austenite and lead brine. So 3 phases exit here. So if you substitute, you will get F equals to 0. Similarly, at this point 16%. Number of phases present, 3 phases liquid, delta and gamma. 2 components iron and carbon. Again you will get the degrees of freedom equals to 0. So degrees of freedom F equals to 0 means neither you can change temperature or composition in order to define this point. You cannot change temperature and pressure simultaneously. In order to define this point, you have to specify temperature and composition, then only you can locate this point properly. That is the indication of F equals to 0. So these 3 points at 0.83% carbon and 727, 4.3% carbon 1147 degrees centigrade, and 0.16% carbon and 1493 degrees centigrade. So all these 3 points, degrees of freedom equals to 0, and we call these points as invariant points. We call these points as invariant points. In iron carbon phase diagram, also you can see there is a eutectic point exists. Eutectic point means the lowest melting point observed, or the system shows lowest melting point. So you can see it here. So this particular point is a lowest melting point present in this iron carbon phase diagram. So this point we call is a eutectic point. and this composition corresponding to this eutectic point we call eutectic composition, and temperature corresponding to this eutectic point we call eutectic temperature. So eutectic composition is 4.3% carbon and eutectic temperature is 1147 degrees centigrade. So this is our eutectic point. So eutectic point means above which we have liquid and below which we have solid. So you can see it here, above which we have liquid and below of this eutectic point we have solid mixture. There is no liquid plus solid region present at eutectic point. You can see it here, off eutectic means somewhere here off eutectic you can see liquid plus solid region exists. Similarly here, liquid plus solid region exists, but exactly at eutectic point only liquid transforms into solid. There is no liquid plus solid region exists. So as far as our topics and heat treatment part is concerned, the transformations which takes place in iron carbon phase diagrams are very important. And most of the phase transformations in case of heat treatment are solid to solid transformations. Means you can see one solid gamma, if you cool at below 727 or 723, it converts into perlite plus ferrite or perlite plus cementite. So this solid to solid transformation means one solid transforms into different solid. So we are interested in solid to solid transformation because in heat treatment we are not going to melt the parts. We are heating the parts and just we are cooling the parts. So means solid to solid transformations are very important, whereas in case of casting, liquid to solid transformations are very important. And as far as the applicability of this high temperature transformation is there, it is a very rare applications are there for this transformation, that is high temperature transformation. So this transformation we call eutectic transformation, where liquid transforms into two different solids, that is gamma plus cementite. So this transformation where one solid 1 transforms into two different solids, solid 1 plus solid 2, we call eutectoid transformation. Eutectoid transformation. And if here at higher temperature, solid 1 plus liquid transforms into solid 2, we call peritectic transformation. Just I will repeat. So liquid transforms into two different solids, solid 1 plus solid 2. So solid 1 is a gamma and solid 2 is a cementite, because both the solids are different. So solid 1 and solid 2. So liquid transforms into solid 1 plus solid 2. We call eutectic type transformation. Obviously, these are a reversible transformation. Similarly, here solid 1 means gamma ion, which transforms into two different solids, solid 2 plus solid 3. Solid 2 is a ferrite and solid 3 is a cementite. So ferrite plus cementite mixture we call perlite, which is a present 100% at 0.83%. So this is a eutectoid transformation. So this is solid to solid transformation, this is liquid to solid transformation. Similarly, this is liquid to solid transformation. So liquid plus solid 1 we call delta N, which transforms into solid 2, that is a gamma. This is a different solid. So delta is BCC, whereas gamma is FCC. So both the solids are different. So again, this is a liquid to solid transformation. So the transformations in iron carbon phase diagrams, you can see three different phase transformations are there: eutectic type transformation, eutectoid type transformation, and peritectic type transformations. And these transformations are very important in particularly solid to solid transformation is very important. So this particular part of the phase diagram is very important as far as our heat treatment part is concerned. So same phase diagram which is given here, but this particular part is very important as far as solid to solid transformations are concerned. So ferrite. So it is a microstructure of fully ferritic structure, obviously. So this is a interstitial type solid solution. It is a solid solution, means there is no phase exists. So you can see only ferrite, and these are the grains of ferrite. So solid solubility of carbon in BCC, maximum solubility of carbon in iron is 0.022 or 0.025 at 727 degrees centigrade. So ferrite is nothing but pure iron because it dissolves maximum percentage of 0.025 or 0.022. Such a low percentage of carbon it dissolves. So almost it is a pure iron. So that's why it is soft. Austenite. So solid solution of carbon in FCC. So maximum solubility of carbon in austenite is a 2% or 2.14% at 1147 degrees centigrade, and it is stable above 727 and it is a non-magnetic. And this phase plays an important role in the phase transformations of steel. Means so this phase is very important as far as our heat treatment part is concerned, because this phase is a parent phase in most of the heat treatment processes. Next is a delta ferrite. Again, it is a solid solution of carbon in a body-centered cubic structure, but at elevated temperature. And maximum solubility is 0.09 to 0.1%, and it is only stable at elevated temperature. So the next important part or microconstituent present in iron carbon phase diagram is the perlite or cementite. Cementite or iron carbide. So it is an intermediate compound or intermetallic compound, and it is also known as iron carbide, and it has the fixed composition or fixed stoichiometric ratio of 6.67% carbon, and it is a brittle and hard phase. And this is the photomicrograph of a perlite, 100% perlite structure, consisting of alternate layers of alpha ferrite and cementite. So light phase is a ferrite, and thin layers, and most of which are dark, are the cementite. So alternate layers of ferrite and cementite. It is just like fingerprint like structure. If you go for thumb impression, so it's just like fingerprint. So we'll discuss more about the iron carbon phase diagram.